Hello everyone. In this session, I'm going to talk about the role that boosting can play when your response variable is binary in nature. So you are doing a classification process, and within that classification, your response variable is a binary. So we can talk about a person having diabetes versus not diabetes, or a person defaulting on a loan versus not defaulting on a loan, a project accepted versus rejected. So these are all the kinds of cases where my response variable is binary, and I'm looking at how I can really use the boosting algorithms which are there as a part of R to really improve or to really bring about a difference in the learning process from the training data, and to create a possibility of improvement in the prediction of the binary outcome. So that is what going as a part of the binary boosting. So here I want to just touch base the conceptual aspect behind the binary boosting, and then we want to look at 6 primary algorithms associated with binary boosting. The most uh, heavily used algorithm, the AdaBoost M1. Then we are talking about the real AdaBoost versus gentle AdaBoost. Then we are also looking at the L2 boost, discrete, real as well as gentle. So we will be talking about all these 6 algorithms. We will apply all these algorithms to one single data set. The data set is the diabetes set, which we have been using for various other aspects as well. We have used diabetes set for neural networks, for support vector machines, for random forests, etc. Wherever we had to predict the binary variable. So here also we would be using the same data set. So I don't want to spend too much time on the data set. So this is our data set, right? The dimensions of this data set are 600 rows and 7 columns. We know that there are some NAs as a part of this data set. We have been using it for some time. So I am removing those NAs by doing the NA.omit. So now the dimensions of this data set is, right now it has 564 rows and 7 columns, and a quick summary of the data set gives me this information. So the diabetes is my dependent variable with negative and positive values, and we are talking about all these as the attributes of the predictor variables: the month of pregnancy, the glucose content, pressure, mass, pedigree, and the age. On this, I want to use the binary boosting algorithms and see to what extent I can do the predictions. I can link the diabetes with each of these 6 explanatory variables and develop a predictive model for binary classification quite effectively. So, getting into the concept of binary boosting, we talk about a discrete ADA boost algorithm. We have already talked about boosting. Boosting is when we are provided some number of observations as a part of the training data, the algorithm will apply different weights to each of these different observations, and based on that a model is built. Using that model, the predictions are typically being done, and based on that it will see which of them are correctly classified and which of them are wrongly classified. Now in the next iteration, those that are wrongly classified, they will receive much more higher importance. So they will receive a much higher weightage, and those that are correctly classified will receive a lesser weightage. Again, a new model is being built. Now that model is again used for the prediction purpose. Again, the correct classified and wrong classified will be taken. Again, the ones that are wrongly classified will receive a much higher weightage. So this kind of iterative approach keeps continuing until the overall prediction of the model typically improves. So if you look at this algorithm here, it's a sequentially generated weighted set of weak based classifiers. So initially we are one single classifier, it's a weak classifier, but because of the kind of weightages that are being applied to each one of them in an iterative fashion based on the learnings from the past mistakes, they are combined to form overall strong classifier. That's the advantage of the boosting algorithm. So the parameters which are used as weights, the parameters which are used as weights, and even the now the solution 1, solution 2, solution 3 is built in an iterative fashion. Now with solution 1, probably there are only 60% of the values are correctly classified, but with 70% are correctly classified in solution 2 and only 40% are correctly classified in solution 3. Now, while determining the final outcome of a variable, this would be given much higher weightage. The weight next, this would be given, the least weightage would be given to this. So the parameter values are automatically adjusted to the data based on the actual performance at each iteration. Even the weights are adjusted based on the actual performance. And finally, to determine the final solution also, the weights are adjusted to get the best possible solution overall. So that is what is going as a part of the binary boosting process. So looking at the methodology part, so let's look at a training data, the same diabetes example. I have different feature vectors. In our case, we have 6 feature vectors, right? The ones that we are considering as explanatory variables, they are all feature vectors. So we have 6 feature vectors and a target which represents the binary class. So we have the variable called diabetes, which is representing the binary class. Now, the role that is being executed by this algorithm is it will try to find an optimal classification, the best possible classification, by making an individual error. So we are talking about an error at each iteration. How many of them are correctly classified versus error is how many of them are wrongly classified. And a measure of that error is by what extent it is wrongly classified. So there is some kind of a measure of an error at each iteration, and that error, which is the misclassification rate, should be as small as possible. So it will try to adjust the weights, it will try to distribute the weights across all the observations in an iterative fashion in such a way that the individual error, which is what is the loss related step, loss function. So it will try to look at the individual error at each of the iterations to be as small as possible. That's the way in which it tries to go ahead in terms of distributing the weights on the features. It keeps repeating the process in such a way that the individual error at each of the iterations typically goes to the lowest or smallest extent possible. And in the process, those observations which are incorrectly classified, they receive more weight in the next iteration, and the individuals which are correctly classified, they receive a less weight in the next iteration. and the weights at each iteration. Right now, how we are calculating the weight? We are saying more weight at one iteration and less weight, especially for those which are correctly classified. Now, how are the weights typically determined? So here we are using iteration specific learning coefficient. So for each iteration, there is a specific learning coefficient. Generally, we represent it with alpha m. So there is an iteration specific learning coefficient alpha m, and this would be multiplied by a classification function. So this is where the different algorithms differ. So classification functions are generally represented by uh, hm of x, the new, right? This kind of an operator is typically used for the classification function. So for we are talking about a learning coefficient which is specific to the iteration. We are multiplying it by a classification function. So it focuses more weight on those objects which are misclassified and attempts to correctly classify them in the next iteration. So that is how the process is continuing. More weight is given to the misclassified or the wrongly classified observation, so that in the next case they get classified correctly. And the classifiers that are accurate predictors of the training data. Now in terms of final selection process, those solutions, those classifiers which are more and more accurate predictors of the training data, they receive more weight in the final selection process, and those classifiers which were not able to do a good job, they will be receiving lesser weight. So even the final selection is not a uniform weighted selection among all the iterations. Those iterations which are able to do a good classification will receive more weightage. Those iterations which were not able to do a good classification will receive much lesser weightage. So now if you look at the different algorithms that we are going to look at from the next slide onwards, so these are the two things that differ. Differences in the nature of the classical boosting algorithms. They are primarily differing in the functional form of the specific learning coefficient. So the alpha m keeps differing. So the specific iteration specific learning coefficient differs across all the models, and even the classification function can differ. So these are the two major differences that you see in the different algorithms that we are going to cover. Just for example, right, let me write some of the differences here, especially with respect to alpha m, which is the iteration specific learning coefficient, and the classification function. When I have to look at these two things, it simply comes out. There are three things that I am bringing out. One is an AdaBoost M1, which is the next algorithm that I am going to look at. This alpha m is being taken as 0.5 times log 1 minus the error function at the iteration m divided by the error function at the iteration m. So this is what is the learning learning coefficient which is specific to this iteration, and whereas n of x is typically taken as the sine function, the sine of x. Whereas when we talk about the real AdaBoost, here this one, the n is typically, instead of sine of x, it would be taken as log of x by 1 minus x, where x is in the range of p0 to 1. So that's where the real AdaBoost is differing. And in gentle AdaBoost, there is another gentle AdaBoost. We are talking about this n of x is simply equal to x. And here the loss function, the measure of this error, also differs across the models, right? Now, when we talk about some of the models, the first three models that I'm going to look at in the next slide, where I'm talking about AdaBoost M1. So if you look at here, the AdaBoost M1, the real AdaBoost, gentle AdaBoost, the way they calculate the epsilon m, which is the error function or the loss function, is the exponential loss function. They simply use the exponential loss function for calculation purpose. So the methods are different, that's it. Whereas these three, they use a logistic loss function. So the loss function is differing across the models. Along with that, the learning coefficient, which is specific to the iteration, is different across the models, and even the classification function is different across the model. But whereas all other things, the way they are doing, the way they are adjusting the weights, the final classification process, the process is the same. The formula that is used for the classification purposes is different across the 6 different algorithms that we are going to take up, but the entire series of steps remains to be the same in the whole process, which means if I know one, from the second one onwards, the only thing I have to be aware of is what are the modifications that I have to do with respect to the first one, so that I can get the second one more comfortably. And after that, how do I do the comparison across all these various algorithms? So now, if I am looking at the AdaBoost M1, I have already talked about it. The loss function is an exponential loss function in this. So the epsilon m is computed as an exponential loss function. The alpha m, which is an iteration specific learning coefficient, is computed as 0.5 times logarithm of 1 minus epsilon m by epsilon m. And n of x, which is typically the classification coefficient or classification function, is typically computed as sine of x. So whether it's a positive or a negative sign. So the sine of x is typically, so it will be either plus 1 or minus 1 depending on the value of x. So this entire thing is actually executed through a package ada. Remember, all the 6 functions that we are going to take up now, all the 6 models that we are going to take up, they are all executed with the same package, same function. So I don't need to load the package again and again, right? All 6 of them are executed with the same package, same function. Only the structure within that keeps differing across the models. That's it. So all 6 functions can quite comfortably be fitted in one single shot, right? If you look at it, I'll explain each one of them, but that's the point, right? We are executing all of them with the ada package using the ada function itself. So let me load the package. I'm loading the ada package. Okay, so ada package is loaded, is installed. Let me load the package using the library function. So here you could see that rpart is also loaded. We will be using rpart as well here, right? So we will have to understand these two functions. One is the ada function. Let's use the ada function first. Let's try to understand what is there in it. Once we understand, we can execute all the 6 models out here. Let me look at the ada. Ada is used, right? First of all, it is fitting stochastic boosting models. ADA is used to fit a variety stochastic boosting models for binary response. Remember, for binary response as described in additive logistic regression. So this is the book. Now ADA is how, this is how I'm giving my inputs to this out here. I have to give either as a formula, you could see here, ADA, I am giving it as a formula. So I have my dependent variable and the independent variables, or the response variable and the explanatory variables. Then I have the data from which the data which I am using for building this boosting model. But more and more importantly, NA dot, okay, in case there are any NAs, I have to take care of this, but the triple dots, the dots here indicate arguments passed to rpart dot control. So I have to give all the arguments that I am passing to rpart dot control. But much more than that, I have to specify my loss function out here. So the loss function is exponential. We have said that some of them use the exponential loss function and some of them use logistic. So I can give the loss function as exponential. The type, again, we have three different types. The three algorithms go with three different types. This one is going with discrete. The next that we are going to discuss will use real. The one that we are going to discuss the next is going to be gentle. So we have a real ADA boost, gentle ADA boost. Iterations, I can leave it to default, or probably I can increase the number of iterations. So these are some of the things that I can typically set, but rpart.control is very important for me. I have to give the rpart.control. So let me just check what will be there as a part of rpart.control, just for quick refreshing. Various parameters that control the aspects of the rpart file. So I can very well define, should there be any kind of a minimum split, the minimum number of observations that must exist in a node in order for the split to be attempted. So what is the minimum number of values in case the splitting has to happen? So if I want, I can set this minimum split. Probably if our data size is small, I prefer a smaller split, otherwise we can leave it as it is. Similarly, min bucket, you can read through the various things. These are more for a splitting purpose. So the CP, which is the complexity parameter, any split that does not decrease the overall lack of fit by a factor of CP is not attempted at all. So this is where I can very well look at, either I can leave them to be the default, or I can play around with all these parameters as such. The max compete, number of competitor splits retained in the output, max surrogate, you can look at all these things. The maximum depth, it is going for 30. If required, I can leave all of them by default itself. The rpart.control, if I want to set it, I can set by changing all these things which are not there as a part of the default, which I don't want them to be a part of default. I can very well change them. Otherwise, I can leave it as it is. Right? So that is one thing that I may have to give as a part of the rpart controls out here. So we have the type, iterations, maximum number of iterations. If I want to test, I can very well check that. And so finally I have to give a control, which is rpart.control. So those are some of the things that I am giving. So let me go back and try to do the basic execution of this model. But before we go back and do the execution, let's have a quick look at the slides. ADA boost is often used with simple decision trees. Simple decision trees come in as weak based classifiers. but when they are combined, the performance is going to improve quite drastically. So as steps, I want the ADA package to be loaded, done. Get the data where the response variable is a categorical binary variable, done. ADA package uses the rpart function to generate the decision trees. If required, you set the rpart controls. Here I am not much interested in changing the default, so I'll leave them as it is, but you have an option where you can change the controls for partitioning the tree. You can really play around with the maximum depth, minimum number of elements that should be there for the splitting purpose, all these kinds of stuff. Then I get into the splitting of the data into a training set and the testing set. So I know that I have 564 observations. So let me take setting the seed to 1,000, and from there let me take train as a variable where I would be randomly picking 70%. So let me take it as 564 into 0.7 giving me 395. So let me pick 395 numbers randomly. So I am taking sample 1 to 564, randomly pick some 395 observations where replace equal to false, which means there is no duplication in the data at all. And from here you take your training data, which is a subset of diabetes, containing those rows which are there as a part of the train and all the columns. Your testing data is again a subset of diabetes, which contains the rows which are not there as a part of the train and all the columns. So I have broken the data into a test data and a training data, right? And now I should also, before I convert it, I think it would be better if I convert this diabetes into negative and positive. Make it numeric. So it would have been better if I had converted the diabetes as numeric. So what we can very well do here is train data, we'll do it train data dollar diabetes. We'll simply say if else, right? We should have done it before the split, but never mind. So if this value is equal to negative, then set it as or probably we can simply change it as dot numeric, as dot character, as dot numeric. Let's see if I can simply say as dot numeric diabetes. Will this work? Let me just check the structure of diabetes train data now. Yeah, diabetes is numeric with 1 and 2. I think that should be sufficient for me. So I'll do the same with test data as well. Test data dollar diabetes. I'll set it as dot numeric test data dollar diabetes. So this is converted into a number, right? The training data and the test data, the diabetes column is converted into a number. So splitting the training data into testing and okay, change the response variable to a numerical scale. We have already changed it by simply making it as dot numeric. Now I can run the AdaBoost M1 model on the training sample, and here I can specify the number of iterations. So let's start going ahead with looking at the model, running the AdaBoost model. So let me call it as fit AdaBoost M1. That's the name of the model that I'm calling. I'm using the ADA function, right? Let me start using the ADA function. The formula. So I require my dependent variable. So or my response variable, diabetes, tilde, all the explanatory variables. So I'm putting a dot to represent all the explanatory variables. The data, I'm simply taking it as the training data. Now, after that, the loss. The loss function for me is an exponential loss function. So I'll set the loss function as exponential. The type here is either discrete, real, gentle. So for this model, I'm setting it as discrete. Then iterations, if I really want to change them, I'll change, otherwise by default they are 50. So let me continue with 50 itself. And the controls, I can set rpart.control. I may not give anything, which means it's a default that I am considering. And based on that, I want to fit my AdaBoost M1 model. Let's see how it gets fitted. Yes, it got fitted. So which means now I can very well look at typing the name of this model. So I'm getting some input out of here. So it's an AdaBoost that has actually happened. This is the formula. The loss is exponential method. Loss is exponential. The method that we have used is discrete. Iterations are 50. And based on that, we have got this as the final confusion matrix for the data. 252 and 102. They are correctly identified. So which means around 354 are correctly identified. 25 plus 16, 41 are wrongly identified. So 41 out of 395 are wrongly identified, resulting in a training error of 10.4%. So there is a training error 10.4. Out of the bag error is around 13.7%. Right, the training error is this much, out of the bag error is around 13.7%. Additional estimate of the number of iterations. So typically it is saying if for the minimization of the training error it took around 44 iterations, and even when it has to reduce it, even when it is based on KAP, the kappa based error, even to minimize the kappa based error also, the typically it took around 44 iterations. We have set the number of iterations at 50, and at around 44 iterations it looked like overall value has converged. But if here the number comes out to be 50, it means that it did not converge properly, which is an indication for me that I have to try increasing the number of iterations out here. So this is what you could see from this output. What are things you are looking at? You are looking at the training error. So the model, when you are applying it on the training data, approximately 10.4% is the error. We are looking at the confusion matrix. So which ones are correctly classified and which ones are wrongly classified. And we are getting different kinds of estimates per number of iteration. Right, you are using the out of the bag estimate. The out of the bag error estimate, it took almost all the 50 iterations. The training error based estimate took only 44 iterations, and kappa based estimate took 44 observations. So probably if required, I want to increase the number of iterations from 50, because the out of the bag error estimate took all 50 iterations. So this is where I want to be slightly careful before I make any kind of conclusion. So that's where I'll set iterations equal to 100 to really see if there is some kind of an improvement that comes to the model. So let me run the model again. Yes. So here it looks like the training error has come down 0636.3%, right? And out of the bag error has come down to 9.6%. But yes, this converged in 98 iterations, fair enough. And the training error and training kappa error also have converged in 95 iteration. So the error rates are much lesser, right? Now I really want to get into the assessment of the model performance. So up to here, if you see, yes, we are looking at these kinds of errors, all the errors along with the estimates of number of iterations that it has taken to minimize this particular error, right? Now we really want to assess the performance based on the testing data. Right now on the training data, it looks like the error is much lesser. So I want to test the performance based on the testing data. Here I want to introduce you to a function called add test. Look at this function add test. So instead of repeating the model, we can simply use this add test function. Let's look at this add test. Add test updates the ADA object. So whatever the object that is already created, it updates the ADA object to have additional testing errors and testing kappa accuracies for each iteration. So this is what I can very well give. So in this case, now what I can do is I'll add the test data to this directly. So what is that I can do? Now I am improving the same model, right? I'll improve the same model by adding the test data also to it. So I'll continue with this same model. The name I'll still continue, or if you want to maintain it separately, you maintain a separate name. But very well, because I'm just updating it. So I'm using this function called add test, wherein x is the existing x, if you see, the object generated by the function ADA. So I'll use the existing object itself, which is fit ADA boost m1. That's my existing. Then it requires test.x. The test.x is new x data. So the new x data is coming from my test data, but it should not contain the 7th column, which is the diabetes column, which is my response variable. So only the attributes I am giving, saying test data, all the rows and minus 7th column. And I am also giving test y, which is also the y values, which will again take the test data but only the 7th column. So that is what I am giving. All other arguments not used by this function. So I can just close it here itself. Nothing much. Now based on this, there is again an improvisation to the existing model. By doing this add, which means initially I have fitted the model. Right? Initially I have fitted one model using only the training data. Now to that particular model, I am adding the testing data as well. So by adding the testing data to that same model, I am getting a new model altogether. And based on this new model, I could see now when I am typing out this one, it looks like I got a different thing altogether. Final confusion matrix. Looks like the final confusion matrix is still more or less on the same lines. 258, 112, even after adding that data, the final confusion matrix looks like more or less maintained. 10 and 15, even this is typically maintained. The out of the bag error is still lying at 9.6, and the additional estimates of the number of iterations. Now you could see the going with the test error, it took only 28 iterations. Testing kappa error, again it took around 28 iterations itself. So the iterations for the training error as well as kappa, they declined drastically from 98 to 95 to 28, right? So the number of iterations it took now, when you have done the addition, it has drastically come down. Now I want to look at both the training error and the testing error for each of the iterations. I want to look at them on the graph. So this is where I'll take the help of, now if I look at here, I think we have done these steps. You have used the add test function to evaluate the testing set. Iterations of the training error and kappa, we have seen that they have declined quite drastically. Now I am ready to plot both the training and the testing error results by iteration. So we had 95 iterations in the first case and 28 iterations in 28 iterations in the testing case. So we really want to see how the error is moving across all these iterations. Now this is where I can use the plot function, where I'll use the plotting of this particular model. But here, if I set test equal to true, which means I want the testing also to be plotted for this particular data. The testing errors also need to be plotted. If you really look at, if I don't give that as an attribute, you could see that only the training errors are typically plotted. I could see that the training error is gradually coming down. But the same graph, if I set test equal to true, so I'm getting both the training errors as well as the testing error. So this is how the training errors as well as the testing errors are existing. We could see that the training error has drastically come down here, but the testing error, I could see that it has come down to a certain extent, but after that it is more or less getting stabled out. So this is clearly showing there is a decrease across the iterations. So boosting can actually learn the features in the data set. So the testing error also came down, but not that much, which has come in case of the training error. The testing error has come down, but not to that extent how a training error has actually come down. And now if you want, you can actually see for each of the iterations also, after each of the iterations, let's say for 20 iterations, 50 iterations, if I want to really look at the summary, right? If you, otherwise you can simply say summary. Let's say you want to get the summary of the model. This summary, it is saying the overall, right? In the overall thing, what it is telling is this particular model, the accuracy in the training data, if it is looking at, the accuracy is around 93.7%, and the kappa of the on the training model is 85.3%. Whereas when it has gone with the testing data, the same model is fitted on the testing data, the accuracy looked like 75%, so almost 25% is the error rate, and the kappa has gone down quite drastically to the extent of 44% itself. So if you want, you can very well check it out for each iteration as well. Now let's say the same thing, if you want to check it for n dot iteration equal to 50. At 50 iterations, what is the scenario? After 50 iterations, still the same, right? Accuracy here is 90.6, kappa is 78 on the training data, but on the testing data it looked like more or less it's the same. So even for 50 iterations the result is the same, but just go with 20 iterations, it may go slightly. So on the training data things are lesser, 86 and 67, but on the testing the scenario looks slightly better. Accuracy is 76.3 and kappa is going to 46. So basically I can check out for different kinds of iterations what is the level of kappa and what is the level of accuracy that is coming out on the training data as well as on the testing data. So I am able to assess how much is the accuracy on the training data versus the testing data. So we are looking at the summary. Using the summary function, I will get all these details. For this particular model, what is the accuracy, what is the kappa for both the training data as well as the testing data. So we are assessing the overall performance of the model on the training data as well as on the testing data. So we are looking at two major aspects, the accuracy as well as the kappa here. Now, if I really want the importance of the variables, I can very well go ahead with the var plot. The var plot is actually telling me the importance of all the variables as a part of this model. So out of all the 6, which one is highly important and which one is the next important. So this var plot is saying that age is a very significant variable out here in terms of classification. Then came the pregnant, then the glucose, then the pressure. The pedigree is coming out to be the least out of all of them. So this is how the importance has been given to the different attributes in the boosting algorithm. And now if you really want to get the scores as well, instead of the plot, if I want the scores, I can simply use the same var plot with the same, but along with that I can also set that the type is scores, so that I'll get the scores. When I say type is scores, I'm going to get the scores here, which talk about the kind of relative importance that has gone to each one of them. Age 0.063 getting the highest, then the pregnant at 0.06, glucose at 0.059, pressure at 0.058, 0.5057 and pedigree at this particular. So we are able to get that these are the kinds of values that are typically being predicted. These are the importance of the values in each of the iterations. So we got the relative importance of each of the variables. Now the final step lies in using the model to the testing data. So wherein I am doing the simple predict, right? I can very well go ahead with the predict function, where I am going ahead with the output, which is my model. So I am using this particular model. I have to do it on the testing data. So I'll give the input as test data without the 7th column. That would be my testing data. And in the type, I want to get both the probabilities as well as the classes. So that's the reason I'll set type is both here, so that I'll get both the probabilities as well as the classification. So now I will get the pred, which tells me two important things here. So initially it has done the classification with respect to 1s and 2s. Along with that, it has also given the probability. What is the probability that it belongs to group 2? 83% here. What is the probability that the second observation belongs to group 1? Almost 98%. Here it is 99%. So we could clearly see what is the probability that the things are going into each of these groups, which is giving us some kind of a clarity in terms of how strong is the classification to that particular group. And based on that, I can very well assess, or I can take my own calls in terms of whether I want to change the grouping or whether I want to continue with the grouping or so on. And even through this method, I should get the same result when I am using my confusion matrix. So if you look at the table where I say pred $class, and test data, all the rows and the seventh column. When I'm doing a table, the confusion matrix that is coming out here, 89, 37, these are correctly predicted. 15 and 28, 43 are wrongly predicted. So 43 wrongly predicted out of the 169, giving me an error rate of around 25.44% on the testing data. So that's how the model can really be used. So probably this may not be the best, right? We might have used some other methods and we might have got some other better percentages of accuracies. We might have got into a scenario where we may have got 80% accuracy as well when we are predicting it on the test data. So it really does not mean that this algorithm will be the best algorithm in all the cases. So it's only a kind of case for us to understand, to try out different kinds of algorithms on the data set and finally select the one that has given us the best kind of a prediction on the data set. And sometimes it would be much more appropriate to work with advanced performance measures like ROCs or kappa measures rather than just simply looking at the overall accuracy of the model or the misclassification error rate, right? So that is how we can very well use the AdaBoost algorithm. Now what I really want to look at is, I would like to make a note of all these codes so that we can quickly redo them for the other algorithms. So all other algorithms, they run exactly in the same manner. So this is where I want to make a list of all the codes that we have written, so that, so this is the one that I want to go with, which is talking about first fitting the model, right? Let me open a notepad. Now all the models will be a straightforward execution for us. So the first thing is fitting of the model. Then we are looking at what the model typically contains, and then we are adding the test data to this model. After that, again we are going ahead with seeing what is the kind of improvement that came to the model after the addition, right? Regarding the testing errors and the training errors, we are going ahead with the plotting, where both the training as well as the testing data are typically plotted. We have looked at the summary of the model, wherein we would get the accuracy and the kappa at all the iterations, right? If required, we can look at the summary at some number of iterations in the middle. And then we got into the process of understanding the importance of the variables in a plot form, and along with that we have got the scores associated with each of these variables in a score form. Either of them is fine with me. Either I can go with the scores or with the direct plot. And once we have got that, we have got into the process of doing the prediction of the class as well as the probabilities of both of them. So I could really assess the probabilities of each one of them, and finally resulting into the table which talks about the confusion matrix. So these are all the same things that are going to continue for all my models from now onwards. It's only the thing is, I would like to assess the accuracy, the overall error rates, kappas, all these things across the models. So now from now onwards, I really don't need to go ahead with the slides, right? The slides are more or less the same. For your understanding purpose, you can very well refer to them. But when I get into the real ADA boost, this is also a discrete boosting, but the exponential loss function again. But when you are looking at the classification function, it uses this kind of a classification function, which is log p by 1 minus p, where p is lying between 0 to 1. So that's the way it works. Now, If you look at the differences that you are bringing in, everything remains the same. The loss is still exponential. The type is, instead of discrete, we are looking at real. That's the only difference out here, right? Instead of discrete, we will make it real. So in the code, what I would make a difference here is I'll change this to real. All other things I am going to keep it the same. So I'll call this as fit real ADA boost, right? Probably just for the name purpose, I'll use it as fit real ADA boost. Fit real ADA boost, right? This is the fitting of the real ADA boost. Let's see if this is improving our prediction. So I don't need to again explain all the stuff, right? We are only making a change out here. Only single change is being made. The type is set to real. Nothing else I am changing here, right? Or probably let me use a generic name that would be more easier so that I don't need to change every time. So I'll call it fit. But this time I'm using a real ADA boost. That's it. Go with that. Right? I'll use a generic name because we are only getting into the understanding process. I'll use a generic name called fit instead of using all these things. Right? Let's see how how this model is going to work for us. We'll go step by step. First, we are trying to fit the one with type equal to real. Right? Probably if you see the steps, it's more or less the same. Quickly just scan through it if you want. Here the flexibilities that we have, remember the flexibilities that we are talking of, you can change all the rpart.control. This is the default rpart.control that I am using, but you can change the maximum depth of the tree, minimum number of splits, all these things you can change. So this is where when you are really using it in the real world, you have so many options to play around with, so many customizations that you can perform, and finally you are shortlisting on that one single mechanism which is giving you a much better prediction accuracy on the training data. Much better coefficients like kappa as well as the ROCs are much more effective. The area under the curve is much more effective compared to the other model. So these are some of the things which are the kind of criteria for you to assess the goodness of fitment of the various models that you are running. So you could see more or less the same thing, right? The stopping the iterations, especially if you are setting the number of iterations, the intention is to control the overfitting. Now if you have seen earlier, when we had executed 100 iterations, it has actually come to the extent of overfitting. The training error has come down quite drastically compared to the earlier case. So if you are having high number of algorithms, there is a possibility of overfitting that is happening, and if you are having very few number of iterations, there is a possibility of underfitting. So which means the predictions could be much weaker on the data. So this is where I have to be careful about choosing the number of iterations. So overfitting in general is a lesser risk compared to that of underfitting. So it's better to set slightly a higher number, though it would be much better for me to set an optimal figure. But yes, compared to underfitting, I'm okay with going with some amount of error with respect to overfitting. So let's execute the model now. See if there will be some kind of an improvement. So I have fitted the model, and the fit is giving me, by the base one has given me the training error is 10.4% still. 256 are correctly classified here, 98 are correctly classified here, 41, 29 and 12 are wrong classifications. Out of the bag error is 137 with 97 iterations. Training errors, the number of iterations based on the training error is 92, based on the kappa is also 92. Now I am going ahead in terms of adding my testing data, the test data to this. I am updating the model with the test data, and after that also when I am looking at the fit, the number of iterations for the test data came down to 73. All other things remained the same. I want to do a plotting of both the training errors as well as the testing errors. So when I'm doing the plotting of the training error, it looked like the training error has drastically come down from this 20 odd percent to around 10%. It has been coming down itself, whereas the testing error, it came down and it stabled out at a point after a certain number of iterations. Probably this is where the testing errors are much lower, right around 60 odd. There is a testing error which is much lesser. Even at 30 iterations, I could see that the testing error is much lesser, but while going with 100 iterations, it looked like the testing error has slightly gone up. Now this is where I have to be more careful in terms of assessing how many iterations are very much required for me. And when I'm going with all these 100 iterations, the summary is telling me that this particular model, right now the training accuracy is around 89.6%, right, only on the training data, so which is lesser than the earlier case. The kappa is only 75 here on the training data, whereas on the testing data I could see that the accuracy is much lesser, only 71% accuracy, when kappa is much more worse. Earlier it was around 44%, now it has come down to 35%. So for this data, the real AdaBoost did not do a good job compared to the simple AdaBoost, right? And when I'm looking at the after the 50th iteration, what is the situation? Things are even more worse. The accuracy has gone to 69% with a kappa of only 28%. So there it did not do a good job. I'm interested in looking at the importance of the variables. So the plotting of the importance of the variables, here the definition is completely different. Probably look like mass is much more an important variable, not the age or glucose. Pressure came next, age is third, glucose is fourth, pregnant is 5, pedigree is still at the last. So if required, I can get the scores associated with each one of them. The scores are nothing but you could see from here also. So the graph is more or less sufficient. I'm seeing that the mass is the most important variable out here. And when I'm going with the prediction part, the prediction has given me that these are the probabilities that are going into each of the groups, and this is the kind of a classification to the group. So the probability that it has gone into group 1 is 27%, probability that it is going into group 2 is 72%. So that's where we are able to classify this particular person as group 2, which is positive to diabetes. Now based on that, I could create a table, and this table is giving me again 91 and 30 are correctly classified, and this 48 are wrongly classified. So going with the accuracy 48 out of 169, the error rate is to the extent of 28.4%. So the real AdaBoost did not do any kind of a good job for me in terms of minimizing the error on the testing data. Neither the kappa is lesser, kappa is very less, which is an indication that compared to the AdaBoost M1, the real AdaBoost did not do a good job in the prediction of the people who can have diabetes versus who cannot have. Now the next model that I want to bring in this context is the gentle AdaBoost. This is also a discrete boosting. It has an exponential loss function, but The classification function is different here, where it takes the classification function simply x. So when it is multiplying it with the iteration specific coefficient, it would be multiplying the value as such with the iteration specific coefficient. Even this is executed with the package ada and the ada function. The only difference that comes in here is the type is gentle. Apart from that, all other things are the same. The type is gentle. So we are simply rest all we are going to keep it as it is. So in our code, instead of keeping the type as real, I will keep the type as gentle. That's it. All else is the same. You could see the slide that I have put is exactly the same. If you want, you can quickly read through the stuff. Right? So in this case, okay, not only for this case, even in every case, the shrinkage parameter new. Here we might set it to point, I mean, if you look at the default implementation, the shrinkage parameter new is set at 0.1, which means the parameter values are changed by that much extent in every iteration. Only if, so if you look at the new, the shrinkage parameter for boosting, default is taken at 1. No, here it is taking the default at 0.1. So that's the shrinkage parameter that we are talking of. By what extent the slow down learning and reduce the likelihood of overfitting. So the learning process happens much slower based on the shrinkage parameter that we are setting. So if the smaller is the shrinkage parameter that you are setting, there is a possibility of drastic improvement in the model's generalization ability. So probably what we can try doing is, for both the cases which we have done till now, let's quickly set new equal to 0.01. Let me just check a very small value of new. Let me quickly go ahead in terms of all the boosts that we have done till now. Right, let's quickly look at all the boosts to see if there is any kind of an improvement in the model. So when I said new equal to 0.01 and gone ahead with the first ADA boost, the training error has actually gone up, right? And training error, now you could see here it has taken all the iterations. So it's better that I increase the number of, if the new is much smaller, I should increase the number of iterations. Let's say I am going with 500 iterations, because 100 iterations is not getting sufficient out here. You could see here the training error and the kappas. Okay, so 497, 479, the training error is 9.4, the out of the bag error is 11.6. So number of iterations, let me set it at 500. Now based on this, I am even adding my testing data. Again, these are all different experiments that we are simply performing. So we have added the testing data, and if required, I should go with the summary of the fit to really see if there is some kind of an improvement. I don't see anything. Training results 90 and 78. Testing results are 73 and 41. So there's nothing much in terms of improvement. But if you really want to see the variables importance plot look like more or less the same, except for it looks like glucose has gone to the 5th position, age is at 1, pressure is at 2, and so on. And now I could have gone in terms of prediction and the overall table now giving me a confusion matrix where 45, 29 and 16, 45 of them are wrongly classified out of 169, resulting in 26% error going ahead with this new. But with our default new, things were slightly more better. Similarly, going with a real ADA boost also, if I quickly want to execute the same on this data, So repeating the real ADA boost. Okay, the training error is still at 13.4 and out of the bag error is at 15.7. Both of them are much higher. I am adding the test data also to the model, and after that I am going ahead in terms of understanding the summary of the model. So in this case again 73 and 40 are the accuracy and the kappa, which did not improve in any case. Even on the training data it came to 86 and 67. Looking at the importance of the variables out here, pressure is 1, the months of pregnancy is 2, probably the pedigree is the least again in this set as well. And if I am going ahead with the prediction and looking at the confusion matrix, in this case it worked out that 92-32 overall, again 45 is the misclassification, 45 out of 169 resulting in the same 26.62 even with this model as well. But now let me try the gentle ADA boost to see if there is some kind of an improvement. So again I am fitting this gentle ADA boost model with the same number of iterations, same value of nu, to see if there is some kind of an improvisation in the overall model. When I look at the fit, wow, the training error has come down quite drastically here, right? It is around 7.8% itself. The number of misclassifications are hardly 31, right? Out of the bag error is around 11%. The number of iterations that it has taken is 447 here, and even the number of iterations going with the training error or the kappa error also is around 482. So there is some hope that this model might be much better compared to the earlier two models, or it could be an overfitment. I have to see once I have added the testing data also to this. Now when I am looking at this, I could see that the testing errors, the number of iterations it has taken has quite drastically come down for both based on the testing error as well as based on the kappa. Now I really have to see how the training errors and the testing errors are lying. I'll have a plot of both of them. Looks like the training error has come down quite drastically out here. And the testing error, yes, it has come down, but after a certain point it has stabled out altogether. So I really need to see the summary. I don't see too big a difference, but when I am looking at the summary of the model, it looks like the kappa is only 39.7% on the testing data with an accuracy of 72.8. So approximately around 27% is the error rate that is existing in the model, right? Approximately 27.8 is the error that is existing in the model. I want to really have a quick check of which variables are impacting the model. Looks like age is a significant impacting, but glucose is very much on the lower side. That is something which is challenging the concept of diabetes altogether. The glucose levels coming out to be the least important one. And I could go ahead with the prediction now of the same. When I look at the predicted values, yes, we get even the probabilities associated with each of the classes along with the groups to which each of them are going to belong to. We can have a confusion matrix on our testing data of 169 observations. Here this comes out that 89, 31, 15 and 34. So approximately 46 of them are wrongly classified out of 169, resulting in an error of 27.2. So even this model is not able to give any better estimate compared to the earlier two models as well. So that's how we can look at the gentle ADA-boost model with some kind of a shrinkage parameter being given. Either I could use the default shrinkage or again I can play around with the shrinkage parameter. Then the next set of models, the L2 boosting models that we are using, the way they calculate the loss function is different. All these three models, everything remains the same. The way they calculate the loss function, they don't go with an exponential loss function, they go with a logistic loss function. That's the major difference between the three models that we have discussed till now and these L2 boosting models. So again we have the types discrete, real and gentle, but this time the loss function is logistic. Everything else remains the same, right? If you can see, all the things that we have tabulated as a part of this is exactly the same, right? So let me just make a small change to the code. Instead of loss being exponential, I'll set it as logistic, and type wise, instead of gentle, we'll start with the discrete, then we'll make it real, and then we'll come to the gentle. So let me start the fourth model out here. This is the discrete L2 boosting model. So we'll see if there is some improvement for this model. Yes, even this model has resulted in a training error of only 7.3% and the out of the bag error of 11.9%. So even on the training data, this model is also done a good job. 260, 106, these are the correct classifications. 21 and 8 are wrong classifications. The number of iterations that it has taken is around 493. Now when I am adding the test data also to this, after that let me see how the number of iterations. Yes, the number of iterations has drastically come down to 42 for the minimization of the training error, testing error. I would like to plot both the training error as well as the testing error out here. I could see that at 42 the error is the minimum most possible out here. The training error has come down quite drastically. The testing error has come down up to here, but again after that it is doing some kind of a dongling. So I could see that this is the plot of the training as well as testing. Going ahead with the summary of the overall fitment, the kappa is much lesser to the extent of 37.5 on the test data. The accuracy is only to the extent of 71.6. So 28.4% is the error that is associated with this model. And let me see which are the variables that are considered as important out here. Pressure came out to be the first, and pathetically glucose came out to be the least in terms of contributing to the overall model. And when I am looking at the predicted values based on this, so it is computing the predictions to each of the observations and going ahead with the confusion matrix, it looked like 48 of them are wrongly classified overall, resulting in an accuracy rate of error rate or misclassification rate of 28.4%. So you could see within this again different kinds of algorithms which use different assumptions for iteration, specific coefficients, as well as the classification functions because of, and even the loss computation mechanisms. All of them are changing and each one is giving me a different kinds of prediction with respect to the overall. Each one is giving me a different kind of prediction altogether. So I can actually get the training and the testing errors, right? We have been doing the training and the testing errors across the iterations. In some cases, I can also go ahead with the training and testing, another plot wherein I can set both the things. If I set two truths, I'm going to get actually two different plots, one with the training error and one training error related stuff, and one based on the kappa. So here the kappa accuracy, if you see, the kappa accuracy is actually going up in case of training, but in case of the testing I could see that the kappa accuracy is actually on a fall. right? So if I put two truths, I'm going to get even the kappa accuracy in my model. So on the training data, it looks that it is keeping on growing, but on the testing data, after a certain point, it is falling. So these are the optimal number of iterations that I have to go with. More number of iterations are really doing an overtraining and a poorer fitment of the data. So I have to be very careful in choosing the number of iterations to typically go with, right? So rest all remains the same. I am looking at the different variables that are influencing the model. All the other things remain the same. So then again, we can very well go ahead with the next one, which is the real L2 boost. Again, all else remaining the same. Instead of discrete, I'll change this to real. This is the real L2 boost. Instead of discrete, everything is changed to real. All other things will remain the same for me. If you look at this, loss function is logistic, the set is type is set to real, control parameters rpad.control, I can do the setting. If you see the steps, they are exactly the same as what we have executed till now in the previous methods, right? Not much of a change at all. So it's better that we can continue the same process altogether and see if overall the estimate of the model is anywhere better. So now going ahead into the implementation of the real L2 boost. So let me see how this model is going to crop up. So we are fitting the model. Fit. Okay, the iterations 489, 493. Training error is around 10%, 10.9%. Out of the bag error. Out of the bag error, we know that it is coming because of the cross validations that are being performed. Looks like around 14.7%. Now I am adding the testing data also to it, which results in the number of iterations both for testing error based as well as the kappa based. 121 iterations for the test data. That is where I have seen that the minimum error is typically coming out. So when you are doing the plotting, you could clearly see that the test error has come down to be the lowest possible here at this number of iterations compared to all others, whereas the training error has been falling. And looking at the kappa, on the training data, the kappa has been increasing like this, whereas on the testing data, after this optimal number of iterations, I could see that the kappa has come down quite drastically. The best way for you to assess is understand the summary. So the point for us to look at here is the summary. We have looked at overall kappa is 40, but if you look at the summary associated with 121 iterations, you will find that the kappa is the highest out here, 44.4. But on the training data, the accuracy is not that great, 83 and 57. But on the testing data, you could see that the kappa has come to the extent of 44.4. This is what is the difference, right? The accuracy also has gone up to the extent of 75.7 when you are using only 121 iterations on the testing data. And going with the importance of the variables out here, look like pressure is the most important variable, followed by mass, glucose, and pedigree again ends up to be the least important variable. Looking at the predictions now, going with this particular model and looking at the confusion matrix out here, it comes out that again 45 of them are wrongly classified, 45 out of 169, resulting in a 26.62% being the error rate of the model, right? So that's how you can typically go ahead in terms of understanding each of the scenarios. right? And I could see which one is giving me the much more higher accuracy would be the one that I would be preferring. Similarly, going with a gentle L2 boost, also everything remains the same except that the type I will set it to gentle. Even if you look at the steps, they are exactly the same. So we can just go ahead by copying the code that we have already saved. Right, the process remains exactly the same even in case of gentle L2 boost. The only thing is the classification function, here it is only X. Apart from that, all else will remain the same. So let me try executing this model on the data. So here the training error is the least when it is 476 iterations. Out of the bag error is also with respect to 494 iterations. We have 8.1 as the overall training error and an out of the bag error estimate of 12% out here. Now I would be adding the test data to this. When I am adding the test data, I can clearly see where the minimum number of errors are coming out for the test data. Probably it looks like the testing error is the least possible, is the least when there are only 5 iterations being performed, whereas the kappa is the highest when there are 26 iterations. Probably I want to check that 5 and 26, right? Whereas with respect, so there is a lot of overtraining that is very much possible on the data out here. Now if I really want to look at the plot, that should be clearly evident for us. The training error is coming down like here, whereas the test error probably looks like it's the least here when the number of iterations are just 5. That is where the testing error has come down. Even the kappa wise, if you see, this is the place where the kappa is the maximum most. So obviously this is somewhere at around 26 number of iterations, right, on the testing data, sorry. So this is where the kappa is looking like the highest, which is around 26 iterations for the testing, whereas on the training data it has been growing and growing and growing. So the optimal number of iterations for with respect to training testing error is 5. Optimal number of iterations with respect to kappa is 26. So now if I am looking at the overall summary of the model, it looks like 40% is the kappa and 73.4 is the accuracy. But the same summary, when I am looking at just 26 iterations, I could see a much better kappa. 50 is the kappa. Accuracy is 77.5. Now this is where I may be interested in redoing the model so that the overall number of iterations become much more higher, the overall accuracy of the model becomes much more higher for a limited set of iterations. Now probably if just for the argument's sake, let's say I am setting this accuracy iterations as 26 and I am redoing the model just for the sake of argument. Right here I could see that the training error is 15, out of the bag is 17 to 24 and 25 out here. Now I will add the test data to this. Once I have added it, now when I am looking at the plotting function, or probably let me just type in the name of the model fit. So here you could see the testing error is minimum at 24 and even the kappa is highest at 24. Now when I look at the plotting of both the error, testing error as well as the training error, you could see that the testing error also has actually come down. The training error has also come down. Kappa also, for the test data it has gone up, and even for the training data also the kappa is going up. And this may give me a much better summary, right? Even if you look at the here it is around 25% only the testing error. But yes, let me just see the summary of the fitment. The summary of the fitment is giving me 74% accuracy with a kappa of 41 if I am going till the last. And looking at the importance of the variables in the process, it looks like age is the most important variable, then comes the pedigree, and the month of pregnancy is going out to be the least important altogether. And I can very well go with the predicted values. Now if I go with the predicted values and I create a confusion matrix, I could see now that the confusion matrix is again with a 45 as an error rate, 45 out of 169 resulting in a 26% error rate. So that's how the model is finally working out. There is a 26% error rate using all these different kinds of boosting models that we have applied. So we really need to see if there is any other algorithm not in the boosting space, or if there are any other solutions that are there which could reduce my testing error and which can improve the accuracy of the classification. So that would be the choice. Otherwise, within these things that are available, or in some cases you may have to change the various parameters, various customizations that are offered as a part of this boosting, so that you can improvise the overall accuracy of the model and reduce the misclassification rate. So this is what is the summary of the overall binary boosting process, where we wanted to use different boosting algorithms for the classification, classification based predictive modeling, where our response variable is a binary variable. Right? We have used 6 different algorithms on the same training data, tested it out on the same testing data, evaluated the accuracies of all the models, and we have done a comparative exercise using all the models. I hope you got a clarity in terms of how we can use the boosting algorithms for the binary classification purposes. If you have any further queries, you can get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.